Hi, in this tutorial, we are going to present an introduction to resistive random access memory. My name is Yiren, my partner Wang and I are going to present here. In computer systems, random access memory refers to the memory that allows data to read or write at any location with the same and fast access time. This type of memory differs from disk storage, which requires a various search time based on the location of the stored data. In the most situations, RAM is used for caching memories, which is the link between CPU and main memory. Depending on the application of the RAM, the design is optimized based on the power consumption, write endurance, physical size, and read or write speed. In order to make some breakthrough on Moore's law pattern, researchers not only focusing on CPU, but also trying to improve the performance of RAM. Any typical memory device is constructed with memory cells, where each memory cell contains one bit of information. The memory cells normally arrange as an array pattern, and they distribute on a grid of word line and bit line. Outside the grid, there are control units, where they process the read and write operations, then sending the voltage signal through the bit line and word line to memory cells. Under a read operation, the amplify unit will generate read outputs from the signal of corresponding memory cells.
So next we'll go over a couple of different types of RAM, starting with the simplest case, dynamic RAM. A single DRAM memory cell consists of a transistor and a capacitor, where the memory location is based on the stored voltage on the capacitor. In many setups, this transistor is a field effect transistor, where the word line controls the gate voltage that is used to bridge the connection between the top of the capacitor and the bit line. And the bit line can be used to set the voltage or read the voltage that is on the capacitor. Here is an example of a substrate with a single DRAM memory cell. In this case, the word line goes from left to right and controls the gate, whereas the bit line goes into and out of the page. And as you can see, the bit line is in series with this NFET, which is in series with the trench capacitor. And trench capacitors are useful because although they take up a little bit of space, they can store a large amount of charge in a very small volume. So let's try doing some operations. To write a 1 to this memory cell, we would want to charge the capacitor, which will require setting the word line to high, saturating the gate, and setting the bit line to high, which would set the voltage of the capacitor. Once we reset the word line to low, we can see that this charge remains isolated on the capacitor until there needs to be read. Now, to do a read operation, we would need to set the word line to high and measure the voltage across the bit line. As can be seen from this picture, there is a limited number of reads that can be conducted on a single memory cell before it needs to be refreshed. In addition, there is a small amount of leakage current to the FET, which means that there is a lifetime for each one of these memory locations, and the refresh step must happen. This property of DRAM means that it can be classified as volatile RAM, meaning that it must be powered at all times, otherwise memory will be lost. Another type of volatile RAM that is commonly used is SRAM, static RAM, which uses a solid-state latch instead of a capacitor for memory location storage. Though this is much faster and consumes less power than dynamic RAM, it takes up a lot more space and is bulkier. Both of these RAMs are preferred for a lot of cases because of their speed. However, their volatility can be problematic. And so there's another classification of RAM called non-volatile RAM, which can be useful for other applications. As it turns out, ReRAM, resistive RAM, falls into this category, as do several other types of RAM, including phase change memory and ferromagnetic RAM. All of these RAM types can maintain the memory location even when power is lost. So what is ReRAM? ReRAM, or resistive RAM, uses resistance states on a metal oxide layer to store a memory value. This resistance state is triggered by voltage, and you end up with two different states, a low resistance state and a high resistance state. Applying a high forward voltage forms a filament called the set step and changes the state from a high resistance state to a low resistance state. This filament can be ruptured with a high reverse voltage, which resets it to the high resistance state. So let's examine the set operation in a little bit more detail to get a better understanding of what's actually going on. If we look at a single oxide state near the bottom electrode, we can see that with an applied electric field, the oxide will actually diffuse to the top electrode, leaving behind a vacancy. This can occur multiple times in a row to create a path of vacancies that actually is conductive. And as it turns out, because it is conductive, the electric field actually increases as this process happens, and the filament propagates all the way across the oxide layer. Now it has been switched to a low resistive state because current flows through this I filament instead of through the more resistive bulk layer. Now the reset operation uses the reverse voltage to collapse the filament. When this reverse voltage is applied, there's an electric field and also added thermal energy from the current that pushes these oxide atoms back to their vacancies, restoring the oxide layer to its original state.
Now we're gonna apply ReRAM to the memory cells. However, if we simply use one ReRAM for each memory cell, we'll suffer a huge current leakage issue. Under this situation below, when we apply a high voltage on write line and different voltage on bit lines, all the current will tend to go through the hugest voltage difference. In order to solve this issue, we required some component to isolate each memory resistor from the outside circuit, just like shown in figure A and B. We're using transistor or BJTs to isolate the memory resistor, just like the construction of DRAM and SRAM. Because of the large property of memory resistor, it's possible to design two-terminal crossbar memory cells. This design eliminates the need for a third reference voltage. This simplified design provides much higher memory cell density and giving the ability to implement two-dimensional memory cells into three-dimensional memory device. ReRAM is a relatively new type of RAM storage, which has many potential applications. The most exciting one is the 3D arrangement memory device with the two-terminal crossbar design. ReRAM could become a high-density, fast, cheap, and non-volatile memory device. However, there are still many drawbacks for current 3D ReRAM technology, such as high cost, manufacture difficulty, high power consumption, and link of heat dissipation. Therefore, there's little possibility for 3D ReRAM replacing current flash drive technology. On the other hand, ReRAM could act as an add-on memory under the DRAM, which has been shown to greatly improve the overall system performance. Thank you for watching our tutorials. Please feel free to email us for any further questions.